Welcome back, everyone, and we'll be starting the second session. And before that, I welcome Mr. Harpreet sir for this session. And Rajeshwari madam, can kindly introduce the speaker for this program, for this session.
Yes, sir. Yes. Good morning, all. I'm very much pleased to introduce our speaker today for the second session. So that is Dr. Harpreet Singh. Harpreet Singh has been working as assistant professor in School of Mechanical Sciences at IIT Goa since August 19, 2019. His area of research includes computational mechanics, impact mechanics, multi-scale modeling of composites, and geometrical modeling of thin structures. Earlier, he worked as a subject matter expert in the areas of mechanics with Siemens Limited, Gurgaon, for 12 years. There, he was responsible for various design verification activities related with strength, high cycle fatigue, low cycle fatigue, and fracture mechanics of rotating and stationary components of turbo generator. Prior to joining Siemens in 2007, Harpreet worked as a scientific officer in refueling technology division of Baba Atomic Research Center at Mumbai and contributed in the functional areas of mechanical analysis and design. Harpreet received his PhD from Department of Applied Mechanics, IIT Delhi in 2017 and also engaged with IIT Delhi Department of Applied Mechanics as a research consultant for DRDO sponsored project in the area of high velocity impact of composite materials for ballistic applications. So on behalf of the organizing committee and participants, I thank today's speaker, that is Dr. Harpreet Singh, for your gracious presence here, sir, with us today. Thank you, sir. Thank you for your presence.
Thank you very much for the introduction. Good morning, everyone. Can you hear me properly, or
Yes,
am I
sir.
audible?
Yes, sir.
Okay.
Yeah.
So
Good.
I would like to thank first of all Professor Kiran and other organizing team and for giving me the opportunity to present some of the interesting areas related with modeling and analysis of structural components. So let me share my desktop first. So okay, my screen is visible.
Yeah. Yes, sir.
Okay. So today
Not the full screen, but it is partial. Yeah. Now it's fine. Perfect. Perfect.
okay. So the topic of my talk is modeling and simulation of structures using finite element methods. So today I'm going to give you the introductory session for FEM approach, means finite element method approach. And let us start with this. So first of all, what is FEM? I think you guys have heard many definitions of FEM. So few definitions I have also mentioned in this presentation. So first of all, I think most prominent definition of FEM is that it is a numerical method for finding out the solution of boundary value problem, which is formulated in the form of partial differential equations. So Professor Mahajan already mentioned in his talk that every physical phenomena, physical means either mechanical, thermal, fluid, or chemical, or any other phenomena, we can formulate in the form of partial differential equations. And along with partial differential equations, if we have some boundary conditions, okay, then collectively we can name this partial differential equation problem plus boundary condition as boundary value problems. Okay, so finite element method means this is one of the technique. There are various techniques available out of those one. Finite element method is most popular method for finding out the approximate solution of these boundary value problems. Okay, so first of all, this one is not the exact technique of finding out the solution of the boundary value problems. This is a numerical method, and this is also an approximate method. Means it is not giving you the full 100% exact solution of the partial differential equation. Okay, there will always be an error in the system, and we always try to minimize that error. Okay, there are various techniques we will talk about how to minimize those ones. So second definition is that this is a method by which we can change the partial differential system or equation system to the algebraic equations. So sorry, I forgot to switch on my video. I think I cannot switch on the camera while I'm sharing my desktop. I think
What can be done?
but that option is not coming on my uh, iPad anyway. So this one, the second definition is this is the method by which we can reduce the partial differential system to the algebraic equation. So those algebraic equations, those will be solved in the form of linear algebra techniques. Okay, so this is the second definition, and the third definition is which is also there in the books or in the literature, that in FEM we divide the whole domain into subdomains. Can you hear me?
Yes, yes, it is audible.
Okay. Okay, and those subdomains, for those subdomains or for those elements, we solve the partial differential equations, and we will form a assembled system, and then we'll ultimately we'll get the solution of the whole domain. So this is the third definition which is there, and the fourth definition is that, or fourth statement which you can hear about FEM is that this is the method which is used for the problems with complicated geometries or loading conditions, as well as complex material properties. Means with those ones we can use this technique. And other one is also there, that it is an analytical technique for solving the complicated problems. Exactly, that is not analytical, but the statement is also there. But it is a numerical technique, I would say, that which is used for solving the complicated problems, which are difficult to solve analytically. Okay. So let us see the history of FEM. Means first of all, history of FEM is very long back. Means in early 1943, in that one that year, R. Courant gave the technique of solving the structural problems using the principle of minimization of the energy. Okay, so this is also called the Ritz method nowadays. So he used that technique for solving the structural problems, complex structural problems, and he succeeded, and which became the basis for FEM. Means we will talk about how that is, but in the next in 1950, from 1950, Boeing team started working on the complex geometries, and how they started means they divided the complex surfaces into triangular subdomains, and they started using the algebraic methods for solving for getting the behavior of those small triangular subdomains, and then they started assembling those one into the large system. So from 1950 to 1960, they worked extensively. The Boeing team worked extensively on this technique, and after that, they started publishing in that area. And in 1960, in 1960, a paper was written, or a research paper was written by Dr. law, and in that one, first time they have used the name finite element, and that subdomains the first time they have named as finite element, and the name of the paper was stiffness and deflection of the complex surfaces. After that, this technique from 19, I think 1980, 60 to 70, this decade, I would say that is the era of FEM. Means in that decade, various techniques related with FEM, those were formed, and a company which is called as McNeil Spindle Corporation, MSC. The name of short form of that is MSC. They developed a FEM code for I think 68K nodes, and that was written with the collaboration with NASA, and they named this code as MSC Nastran. So that became very popular during that era, and after that, in from 1980s to 1990s, various agencies or various other research organizations, they started working on this one, FEA, and they also combined various CAD techniques which are available with FEA, and they I would say that is in that period, they merged the FEA and CAD into one platform, and they used for solving the various structural problems. So after that, nowadays it is very common, easily available packages we can find in the market which are there, and we can use those FEM packages for solving the complicated structural problems. So next is, what is the origin of FEM? Means how, what kind of problems we can solve using FEM. So first of all, I would say that fundamentally, if we see the origin of FEM also, and the history of FEM, first of all, it was used for solving the static structural analysis problems. So I already talked about that one. Means in that problem, in those problems, we try to find out the deformation, stresses, strains, reactions, and energies of the system, means of the full domain. And the second type of problems which we can solve using FEM is the dynamic problems. Dynamic problems means the load in those problems is a function of time, and in those problems we usually are interested in finding out the frequencies, mode shapes, and stresses, sometimes stresses and strains, and then those we can compare with the endurance limit, and for the rotary systems, we also generally are interested in finding out the reactions and energies of the system. So apart from that, in the heat transfer side, we are generally interested in finding out the temperature of the domain, or temperature variation in the domain. So those can also be found out by using FEM. And apart from temperatures, we can also find out the heat fluxes through various surfaces, as well as thermal gradient in the system, and heat flows from one component to another in the multi-component system that we can find out. So fourth commonly used area for FEM is fluid analysis. Means in that side, we generally are interested in finding out gas pressure, temperature of the gases, and velocity of the gases, and some conjugate problems or multiphysics problems. We are also interested in finding out the convection coefficients. So all these parameters, or all these unknowns, we can which are mentioned in the slides, we can find out using FEM techniques. Okay, so this is only in the line of interest of mechanical engineering. Apart from that, FEM can be used for electromagnetic problems also, or for chemical reactions problem also. Means various other areas are also there where this technique can be used. Okay. So let us focus on solid mechanics problems or structural problems. So on the basis of loading, here I want to mention about the spectrum of what kind of different kind of problems we can solve using FEM especially in case of solid mechanics. Okay, so solid mechanics problems based on the loading type we can divide into two categories. One is static problems, other one is dynamic problems. So this shows the static side and this shows the dynamic side. So apart from that, this is based on the type of loading. Means if the loading is function of time, then we can say the problems are lying in the area of dynamic side. And on the if loading is constant with respect to time, then it is called static problems. Okay, so this is based on the type of loading. Apart from that, if we see the behavior of the solid domain, so on the basis of that, we can divide also these problems, structural analysis problem, into two categories. One is called linear, other one is called non-linear. Okay, so in the linear side, the behavior of the solid is, we would say, that is linear with respect to applied load. Means the reaction or the response which we are getting from the solids, those will vary linearly with the applied load. Okay, but in case of non-linear, we can see the relation between applied load and the output which we want to get from that one, or deformation precisely, that will not be linear, that will be non-linear. Okay, but these non-linear problems we can further divide into other various categories. Means first of all, first kind of nonlinearity is called geometric nonlinearity. In this category, we can also further subdivide into three. One is called contact nonlinearity, other one is large deformation nonlinearity, other one is the third one is instability. So geometric nonlinearity comes into the picture when the deformation of the system that becomes very large, and that makes the domain as a new domain with respect to applied load. Means at each time step or each load step, you will get a different domain, means which is not matching with the original domain. Then we can say that the problem is lying in the nonlinear category, and that is called geometric nonlinearity. Okay, so that's why you are seeing the name, especially the large deformation. And inside in case of contact, the deformation is also causing the change in the domain. When two bodies are generally are in contact with each other, due to the deformation, the shape of the domain that become different than the original domain, and then we can say that it is not matching with the original domain. So that's why this is coming as a nonlinear system. So in the second category, in the linear side, is the fracture one. So due to the fracture, sometimes domain boundaries, those will increase. Means the whole system that will become different than the original system. So that's why the behavior of the new system will not match with the original system. That's why the nonlinearity that will come into the picture. So apart from that, sometimes the material, the inherent material that behaves nonlinear, and further we can say, I think you might have heard about plastic materials, where you can see the large deformation and permanent deformation. Those are lying in these categories, and due to the damage inside the material, sometimes the material will start behaving nonlinear. Okay, so further we can also divide this material nonlinearity into two categories. One is rate independent, other one is rate dependent. Okay, so if the material is function of rate of applied load, then it is called rate dependent load, where the viscous effects those will be present in the system. And other one, if that is not dependent upon the rate of the applied load, then it is called rate independent system. Okay, so this subdivision is on the basis of behavior of the solids. Okay, or behavior of the material or the system, I would say. So apart from that, we can also subdivide a solid mechanics problem based on the geometrical classification. Means based on the geometry of the system. Sometimes some systems we name as 1D systems. Okay, some system we name as 2D system, and sometimes we name as 3D systems. Okay, in 1D systems or 1D structures, generally you will see the problems of trusses, cables, and pipes. Those are coming in this category. And in 2D structure side, we can see the plane stress, plane strain problems, or plates or shells problems. These are called, these are lying under the category of 2D structure problems. Okay, in 3D structure problem, rest of the structure means apart from these one, we call those one as 3D structures, which are not lying in plane stress, plane strain, or axisymmetric, or plates or shells problem, or trusses, or cables and pipes problem. Those are called 3D structure problems. So first of all, I want to also highlight here that all these problems nowadays can be solved using FEM technique. So you can see the capability of FEM means all the domains which are written here, or all the categories which are written here, those can be solved. The problems lying in those categories can be solved using FEM. Okay. So what are the typical steps we follow in case of FEM? So here I am going to mention about following steps. Means there are 6 steps which we follow in case of FEM analysis. First of all, we discretize a domain into subdomains. First step is named as discretization. So in that step, we discretize the domain into subdomains. Okay, the subdomains, especially those are called elements here. Okay, and the process of discretization whole that is called as meshing. So we have various tools available, means apart from FEM techniques, FEM solvers, we have other tools which are used for this purpose. Means just like, have you heard about, I think you might have heard about this one, hypermesh or gmesh. These softwares we can use for discretization of the bigger domain into subdomains. Okay, and these subdomains are called elements. So second step, which is named as developing the elemental equations or elemental governing equations. In that one, what on the basis of those subdomains or shape of those subdomains and the order of those subdomains, we develop or we write the elemental level governing equation for each element. Okay. So in the third step, which is called assembly of the system, there we applying the compatibility relations. What we do, we combine the elemental level equation into a assembled system equations. Okay, so for combining those ones, generally what we do, we first of all we give the numbers of the subdomains as well as the nodes. Means nodes are the corners, means or the connecting points of the elements. Means I think we will talk about later about nodes, but on the basis of those numberings as well as compatibility relations, we generally assemble the elemental system as a assembled system. Okay, so next is application of boundary conditions. So next we will apply on the assembled system, we apply the boundary conditions which are given to us. So those boundary conditions can be can lie in the category of Dirichlet boundary condition or Newman boundary condition. But for structural problems, we would say these are called as displacement boundary conditions and the force boundary conditions. Okay, so this is the generalized name for all categories with Dirichlet and Newman boundary conditions. We apply those one for the assembled system. After that, what we do, we will use the linear algebra methods for solving the algebraic equation for getting the values of primary variables. Okay, so in case of structural problems, generally we have the displacements as the primary variables, or for heat transfer problems, we have temperatures as the primary variables. And so after getting the primary variables, in the next step, where we generally are interested in calculating the secondary variables. The secondary variables are for structural problems are in the form of stresses, strains, or reactions. Those will be calculated afterward, means after calculating the value of the primary variables. Okay, so these are the typical 6 steps which we follow in case of FEM. So now let us talk about FEM based flow process. Means flow process is design flow process. If you want to design a system, what are the steps you will follow where you can use the FEM technique? Okay, first of all, what we do in this case, we define the problem statement. Okay, that problem statement that will be in the form of a domain size as well as the other parameters. For example, the boundary conditions, the material properties, uh, uh, or time dependent material properties. These will be the part of problem definitions. Okay, so this, after getting all the information regarding the problem, so what we do, we supply that information to the preprocessor. Okay, the preprocessor means in the preprocessor, the information which is passed to the preprocessor, that will be used for further processing. Means the material data that which is there. For example, in case of structures, we gave elastic modulus, Poisson's ratio, density of the material, or sometimes if we want to analyze the plastic material, then we give the yield strength or the hardening modulus or other things. So these material data that is supplied in pre-processing stage of the FEM. Okay, and after getting all this data regarding the material as well as the boundary and loading condition, what is being done in pre-processing stage, they will use this data to form the elemental or assembly level equations. So uh, apart from that, processing the data, what comes in under pre-processing is the meshing of the whole domain. In meshing, I already talked about this one. In meshing stage, what we do, what we subdivide the whole domain into subdomains, and then we assign some numbers to the subdomains or particular nomenclature to the subdomains. And after whole package, meshing, material data, boundary condition, this will be supplied to the supplied to the solver. Okay, the FEM solver. So in FEM solver stage, what generally that is being done is they inside that one, they generate the element shape functions, transformation matrices, and then using those transformation matrices, the local data that will be transformed to the global systems, and after that elemental governing equations, those will be written, and then the based on the numbering which is coming from the preprocessor, that is used for the assembly of the those elemental level governing equations. And after that, we apply the boundary conditions. After applying the boundary condition, the whole system, which is reduced system, what we generally do, we process that equations or reduced system for getting the solution of the system. Okay, so here we use the various linear algebra techniques which were mentioned earlier also in the previous presentation, in the form of Gauss elimination method or other methods. Okay, so after getting the values of primary variables, all the primary variables along with the meshing data, that will be supplied to the post processor. Okay, in the post processor, what we do, we plot the data to get some kind of visualized sense. Apart from that, we process the primary variable data to calculate the secondary data, just like stresses and strains, factor of safeties, or other secondary variables. And after getting all the secondary variables and all the data which is required for the designing point of view, what we do, we will compare the calculated data with the acceptable limits. Okay, so if we found that if calculated data is under the limit of acceptance, then we can say the system is okay. Okay, the design is okay. Okay, then we can say we achieved. Suppose in some cases that is not meeting, then what we do, we reiterate the problems. We can change the domain of the problem, or we can add some material at some of the critical sections, or we can change itself the material properties, or we can use the new material. That is also possible. And then we redo all the process, means pre-processing and solver and post-processing. So all the things will be checked again. Okay. So next we will talk about the basic terminologies which is being used in case of structural analysis. We have already seen that that we generally write the partial differential equation for a structural domain, and though in that differential equation we generally see these variables, means we see forces, we see tractions, we see point loads. F is first one is forces or body loads or volume loads. Second one is tractions, which are surface load, and third one is point loads. Okay, and all these those will be used for formation of the partial differential equation of the system, which will be which we call that the equation of equilibrium, which we see in case of structure that will be in this form, means sigma ij over j plus fi equal to 0. That will be the equilibrium equation for the structural problems. And sometimes we also see that boundary conditions in the form of the displacement is in some of the portion is 0, or displacement at some of the boundaries or some of the subdomains that is constant. Okay, this is especially the displacement boundary conditions. But one thing that we can also mention here, that sometimes we also see the forces, those are specified on the boundaries. Okay, either in the form of point loads, traction loads, or body loads. Okay, so these are the terminologies which are used for the structural problems. Apart from that, how we can process this one, we have various methods. So the methods which are very famous, those are the Galerkin's method and the Rayleigh rates method. Rayleigh rates method, that is nothing. It is another form of a principle of virtual work for basically structural mechanics problems. So these two are, first of all, these two are the approximate methods for finding out the exact finding out the solution of the partial differential equations. So either of these two could be used for finding out the solution of the partial differential system, and these are the fundamental framework for the finite element method. Okay. Today I cannot explain these two in details, but there are various other approaches or simplified approaches which can be used for understanding the FEM FEM technique. So that I will explain slightly in more detail. So I think I talked about find elements, nodes. So what are these ones? So nodes are nothing but these are the specific points related to the finite element, particular element, where we want to see the values. Means we want to calculate the values of the primary variable as well as the secondary variable. Okay, these, I would say, these are the point of interests. Okay, and apart from that, we have during those ones, we will also listen about shape functions. So what are those shape functions? These are the interpolation functions. So as I told you, FEM is an approximate techniques. We are using some kind of interpolation functions or approximate functions for finding out the values of primary variables. So these shape functions are related with those ones. So I have given the example here also, that suppose we want to find out the value of phi, which depends upon x and y of the x and y coordinates. So this we can write in the form of shape functions n1, n2, n3. These are the three shape functions, and phi1, phi2, phi3. These are the values at some specific points, means those points are called nodes. Okay, so I think I will also explain more about shape function in the next slide. So uh, apart from that, you will also listen about degree of freedom. Okay, so degree of freedoms. What are the degrees of freedom? Means these are the independent variables associated with each node, or sometimes we also associate with the element also. So number of the variables which are defined the state of the system per node is called degrees of freedom. Okay, and sometimes we also combine the whole the nodes, all the nodes of an element, uh, and take the sum of all the degrees of freedom, and we can say that that is the degrees of freedom of that element. Okay, but this is not the right approach. But um, uh, degrees of freedoms are more about more related with the nodes. Okay, and apart from that, we also listen about the stiffness matrices. Okay, the stiffness matrix is what means it is the matrix which contains the information about the geometry of the system as well as the material behavior of the system. Okay, so based on this data, we are getting the response of the system. Okay, so I think this will be more clear. So let us use a simplified approach, which is called direct stiffness method for understanding the FEM. Means this is this whole method we can relate with FEM, and we can say this is the method which is being followed behind the FEM technique or FEM softwares. Okay, so first of all, what is happening in case of direct stiffness method? Uh, we can start start the understanding of direct stiffness method by taking a simplified spring element. Okay, this is a spring which is shown here that is having stiffness K. Okay, and the length of the spring is L. And on one side, I have named this side as 1. Okay, one end is named as 1, and other end is named as 2. Okay, at 1, the uh, the degrees of freedom now I can assign. Means suppose this is only 1D system, it can move only in one direction. Okay, so then it will have only 1 degree of freedom per node. This 1 and 2, we can say these are the two nodes of the system. So so U2 is the degree of freedom which is there at the node number 2, and U1 is the degree of freedom which is there at the node number 1. Okay, and U1 and U2 both are the primary variable of the system. Okay, apart from that, we can also see that there are forces which are there on these two nodes. F1x, that is the force which is applied at node number 1, and F2x is the force applied at node number 2. Okay, due to application of this node, the spring will either that can elongate or that can compress. Okay, but the behavior of this spring we can get in the form of this equation, which is T equal to K delta. So this also shows that the elongation of the system or compression of the system that is linearly related with the applied forces. So T also stands for the tensile force, okay, and delta is the relative displacement between the ends, and these two are related with each other by this spring constant. Okay, spring constant is the material property of the or the stiffness property of the system. Okay, so if I use this equation further, and if I expand this one, I will get T as T equal to K U2 minus U1. So delta, which is relative displacement of the ends, we can expand in the form of U2 minus U1. So U2 is here. I'm assuming that U is moving. U is larger. U2 is larger than U1. So that's why we are getting the elongation of the system. Okay, so suppose what we can do, we can use this equation for relating our applied forces F2x and F1x with the displacement. So F2x shows that which is force applied at node number 2, that is related with K into U2 minus U1, And similarly, minus of F1x is related with K U2 minus U1. Okay, so K1x, the direction of K1x, that will be opposite, means in case of elongation, the applied force that will be in the direction of minus x direction. So that's why this minus sign is coming here. Okay, so if I use these two equations further, which are written here, and if I change these two coupled equation in the form of a metric equation, I will get this matrix system of matrices. Okay, and in this system of matrices, first one is coming as the force matrices, which is the column matrix, and the other one is the stiffness matrix, where you can see all the stiffness value or spring constants are written, and the third matrix is third matrix is coming as the column matrix, which is the degree of freedom matrix. Okay, so this matrix equation, or this system of equation is giving us the behavior of the system. Okay, so how this system, the spring system, that will react after applying the forces, means of forces we can apply as F1x, F1x and F2x. Or ultimately applying these forces, we will get the response of the system as U1 and U2. Okay, so further we will assume this system is a linear system. Okay, the K is constant and the forces and displacements, those are related with each other in the linear fashion. So if I use that assumption, then I will see that my displacement from U1 to U2, that will vary linearly. Okay, so after applying this linear variation assumption, if I use the boundary conditions, means suppose on one end I'm naming this one as 0, and on other end I'm saying the value of x is at that end is L. So if I use these two boundary conditions, what I will get, U1 as A1, A1 as U1, and A2 as U1, U2 minus U1 divided by L. Okay, if I put these two values, I will get my U in the form of, which is initially I assume that U is equal to A1 plus A2x, that will be changed as U into N1, N2, this one, the row matrix multiplied with U1, U2, this is the column matrix. Okay, so N1 and N2, these are called the shape functions of the system. Okay, so the exact form of N1 will be 1 minus x over L, and N2 will be x divided by L. So these things you will you can relate, means when you listen the shape functions somewhere in FEM literature, these are these two things you can keep in your mind, means these shape functions are used for defining the approximate function of the primary variable. Okay, so after, now we can put this one aside, and we can come back to our original system. This we can ultimately write as in the form of this elemental level governing equation. This is F, which is capital F matrix, which is nothing but F1x, F2x, the column of that one, the column matrix of that, and other one is K matrix, which is stiffness matrix. We already have seen that this is in this form, and the degree of freedom matrix, which is U1, U2, and that is column matrix. Okay, so ultimately this equation F equal to KD, that is called elemental governing equation. Okay, so I talked about assembly, means after dividing the whole domain into subdomains and getting the governing equation of each element or each subdomain. Now we can talk about the assembly, how we can do the assembly, how we can combine the two separate elemental equation as the one system equation. Okay, so for that one, let us take the example of two springs. One is called as number one, other one is named as number two here, and these two are attached with each other, and these are the boundary conditions which are applied. Means on one side I am fixing the end, and on other side I am applying the force as F2x, and in between also I am applying the force as F3x. So these are the forces which are acting. These are the loading condition precisely, and this one is the boundary condition. Okay, so now if I see these two systems, the whole system, that I can also analyze separately, taking each spring system individually. Means just like I have taken the one system as this spring, and where the forces which are internal forces which are acting as F3x1 and F3x2, these are equal and opposite to each other, so that those will be cancelled out, and only the F3x that will act. Okay, so on this system, I will not go into to the detail, but on this system, if I apply the force equilibrium or force balance equations, I will get all the equations in this form. Means F3x that will be equal to F3x1 and F3x2, and F2x, which is applied force at second node, that will be F2x2, and F1x, which is the reaction force acting at this point, that will be F1x. So these forces
Kiran sir.
Sir, what happened, sir? Total, no. Hello, sir. This link has gone. There is no link. Something is happened, please. Kiran, sir. చెప్పమ్మా ఎవరికి ప్రియా మేడం వెళ్ళిపోతుంది వాళ్ళ అబ్బాయిని తీసుకునేటానికి అంతే కదా ఓకే ఎంజాయ్ ద డే నేను హాఫ్ డే తీసుకున్నప్పుడు పోతే 5:30 అవుతుంది నాకు
Hello, can you hear me now?
Yeah, yes.
Hello.
Yes, it is audible.
Okay.
Sir,
Sorry about
presentation,
this
sir.
one.
But presentation
Yes,
is
yes.
not more. Yeah, okay, fine.
Yeah, it's coming now.
Yeah,
Can you
thank
see
you,
now?
thank you, sir. Done. We are seeing your screen.
Okay.
1D finite. Yeah.
Okay. So earlier we talked about direct stiffness method, means that is being used earlier, means in 1950s or 1960s for the analysis of structures. Sorry. Have you? I think I talked about this one, but I was not sure, means whether that you have listened about this one or not. But now I'm talking about this. I was not aware, means when my connection was disconnected. Anyway,
Okay,
so
sir.
this one here now we'll talk about 1D finite element truss element. Okay, now we can relate our direct stiffness method with the finite element method. Means earlier we have seen we have F matrix, we have stiffness matrix, we have degrees of freedom matrix. So stiffness matrix, how that we can relate in case of suppose I'm taking a truss or I'm taking a bar. Okay, so stiffness, how I can get the value of stiffness for the bar. So for the bar, we have this one constitutive relation sigma x equal to E epsilon x. Okay, so this one sigma x, I can replace this one as the force as a area into sigma x. So that will be I can replace my T as area into sigma. Okay, so this can be replaced, and further if I used my relation of this one, the sigma, if I replace this one as in sigma, if I replace sigma x with E epsilon x and I replace epsilon with U2 minus U1 divided by L, I will get ultimately this form of equation. Okay, what I'm doing, I'm replacing sigma, in this equation I'm replacing sigma with the E into epsilon x, and epsilon x, I am saying this will be U2 minus U1 divided by L, change in length divided by L. So ultimately I will have this system of equation. Okay, so if I compare this one with my previous direct stiffness method, I can say that I will have the stiffness in the form of AE divided by L. Okay, that will be the K here. So now I can directly replace my K in the previous equation of springs with AL upon E, AE upon L, and I'll get this form of my elemental level governing equation for truss element. Okay, so here I can say that my stiffness matrix is AL upon E, and 1 1 1 1, these are coming at 4 places, so this will be my stiffness matrix. Okay, so this is about the truss element, which is aligned with x-axis. But if I want to use this truss element for analyzing the problem, for example, this problem of analyzing this structure, large bridge, or other one is this one. But here I can see all the elements which are there. This one, these are not lying along the x-axis. So these are inclined with x-axis. So how can I use my truss element, which is only I have formulated only for the x direction displacements. So here I will use the transformation matrices, okay, the transformation of coordinates. So I think you might have heard about this one in your mathematical courses, that how we can transform the variables from one coordinate system to another coordinate system. What we will have the transformation matrix. That transformation matrix will be in the form of cosine theta, sine theta, and cosine theta. This will be the transformation matrix, and by multiplying the one system of the primary variables in one coordinate system with that transformation matrix, I will get the new primary variables in the other coordinate system. So now I can I can replace my capital D or degrees of freedom matrix with the T inverse or T inverse D dash. Okay, or I can use my same truss element along with the transformation matrix for any orientation of the 1D structure. Okay, so transformation matrix we have seen in case of simple two-dimensional problems, that is coming as CSSC. But for generalized truss element, means for three-dimensional problems or for other problems, this will come as CS0000CS, because in each node we will have for two-dimensional problems or for inclined truss problems, we will have 2 degrees of freedom, means U1, V1, U2, V2. Okay, so this we can use along with my degrees of freedom matrix for the calculation of new degrees of freedom in the new coordinate system. So same thing I can use in case of forces also, where I have the force matrix transformations, and then I can use the same technique for the transformation or for transforming my stiffness matrix. Means here I will multiply by T dash K T dash T. So I in this case also I will transform the stiffness matrix, which is aligned in x-axis to any generalized inclined inclination of the coordinate system. Okay, so ultimately I will have K matrix or stiffness matrix in this form. Okay, this is about the truss elements, where the displacement, where the stiffness is only the direct stiffness. But we have the structures like this one. I think electric poles you might have seen, or maybe the buildings where the skeleton, skeleton of the building we can analyze using this one-dimensional FEM approach. Okay, so here we will have the degrees of freedom per node. So apart from the displacement, we will have the slopes also. These two the rounded arrow. These are showing the slopes of at each node. Okay, so these additional degrees of freedom that will change the truss element formulation. Means we have to introduce more degrees of freedom in the system, and as well as more more material data as well as the geometric data into the system. So in that case, we will name our new element as frame element. Okay, in this case, our stiffness metric, that will be in the form of this. Means okay, here EI upon LQ is the bending modulus. Means the bending properties, those will come into the picture. I think you have also seen these kind of system while analyzing the beam problem. Okay, so further, if sometimes our two nodes, those will not be sufficient, so further we can introduce more complexity in the form of increasing the order of the system. Means if I have the two nodes, okay, so I can say this one is my lower order element, and if I have the 3 nodes, I can say this one is my 3-noded element. Okay, so this is higher order element, this is lower order element, means approximate functions which I have used in case of direct stiffness method, which is u is equal to a0 plus a1x, that will not remain same in case of 3-noded element, means one more term that will come into the picture, means a0 plus a1x, which I assumed in case of linear element, that will be a0 plus a1x plus a2x square, that will be there in case of 3D element or 3-noded element. Okay, so this is all about the 1D FEM which we have discussed till now. Apart from that, we sometimes our 1D approach, means our 1D structures assumption, that will not remain valid in some of the cases. Means if we use that approach for analyzing the structures, then we will have a lot of error in the system. Then in that case, what we generally do, we will replace our 1D system with the 2D system. Just like I discussed, we have the plates, we have the shells, which are coming in this category of two-dimensional structures. Here, am I audible? Hello.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Sometimes I listen to the sound, means just like I got disconnected. Anyway, so I was discussing about this one. So here, in case of plates and shells, what we will have different kind of elements. Means we have triangular shape elements, and we have quadrilateral elements. Sometimes we can also say this one special one, the rectangular elements. These are the elements which are there for two-dimensional approach of analyzing structures. Okay, so here also we can see there are 3-noded elements and there are 6-noded elements. And similarly, in case of quadrilateral, we have 4-noded elements and 8-noded elements. So the lesser the node numbers, the count of the nodes, the lower the order of the element. Means just like 3-noded element, that is lower order element, and just like 4-noded quadrilateral element, that is also lower order element. And if we want to increase the order of this one, we have to put more nodes on each sides. Okay, so 6-noded element is higher noded element, and 8-noded element, quadrilateral element, is also higher noded element. Okay, so first, next, we can also discuss about, means how we can, what kind of problems we can name those one as 2D element, 2D structural problems. So apart from plates, shells, which are visually we can see those are 2D structures. We have other approaches for defining the 2D approach, means that is plane stress approach and the plane strain approach. So these are the two conditions on the basis of we can say that a generalized 3D problem we can analyze using the 2D approach. Okay, so in case of plane stress approach, what we do, what we have, how we can apply the plane stress approach, means for the reduction of 3D problem to the 2D problem. So if we have a domain whose outer plane thickness or outer plane dimension that is very less as compared to the in plane dimensions, then we can say that that one condition of assuming the plane stress condition is fulfilled. The second condition is there should not be any outer plane loading. Okay, and the loading should be only function of x and y. So this, if these two conditions are fulfilled, then we can say this is the plane stress problem. And here, what will happen? We have the relation between sigma and epsilon, and sigma and epsilon are related with each other with this constitutive matrix. So this, for plane stress approaches, we have this kind of constitutive matrix which can be used, and this 3D structure we can analyze using the two-dimensional approaches. Means only the cross section we will model that one, and we will apply the loads, and then we will get the deformation or stresses. So other category is of plane strain problems. What is happening in case of plane strain problems? We will have one dimension or outer plane dimension that will be very large as compared to in plane dimension. I think you might have seen the classical example of in this category is you have seen this dam problem. Okay, where the cross section or where the third dimension cross section is very small, or third dimension is very large. Out of plane dimension is very large as compared to the in plane dimensions. So in this case also, apart from the geometrical condition, we have the loading conditions also for the assumption of plane strains. So first is that out of plane loading that should not be there. Means we should not have the loading in that direction or in the direction of large dimensions. And the loading that should not be function of z, or z means this one, the direction of larger dimensions. Okay. So in this case, the D matrix that will be in this form, means only the D matrix that will change respectively in case of plane stress and plane strain problems. And apart from that, what we have to do we have to model the cross section in FEM, and then we have to analyze that one. So this is how we can reduce the 3D real world problem to the 2D problems. Okay. So I will briefly talk about the triangular element formulation here. Means the triangular element which I have shown earlier, means those can be used for 2D FEM. So here what we'll have, each node we will have 2 degrees of freedom, U1 or U and V. So what we will do, we will separately assume that U is function of or U, this form of approximate function for U, and this form of approximate function for V. Means in this approximate function for U, we will have these three shape functions, and apart from that, we will have U1, U2, or U3, or Ui, J, and M values of unknown variables at these nodes. I think that will be too much for, but we can assume that we can see that the shape functions also, those are being used for the formulation of two-dimensional triangular element. Okay, so again I can use further this form in the form of matrices, means so that I can apply the linear algebra techniques. Means, and further if I more simplify these matrices or this metric equations, I will have psi as psi means the degrees of freedom matrix. Sorry, D is the degree of freedom matrix. Psi is the approximate function matrix. This we can write as psi as equal to shape function into the degrees of freedom matrix. Okay. So apart from that, we will have, in case of two-dimensional triangular element, we will have the shape function, this one, strain displacement relationship, where the B matrix is called strain displacement matrix, and these two collectively, psi functions as well as epsilon BD, which is written in this form, those collectively we can use for the formulation of our stiffness matrix, force matrix, and degrees of freedom matrix, which is already there. Means these two along with that we can use for our final formulation of the triangular element. Okay, so I think details I cannot talk about this one. Anyway, after getting the values of degrees of freedom matrix or solving the primary variables using FEM, this is how we can calculate the secondary variables, means either stresses or strains. The strain will be B into D. Okay, this is strain, and if I multiply strain matrix with D, I will get the stresses for each element or at each node also. Okay, so apart from that, we have symmetry and anti-symmetry boundary conditions for reducing the problems. Okay, so in symmetry and anti-symmetry boundary condition, what we will have, we can, instead of modeling the whole system, if the system is fulfilling two conditions, means one is the geometrical symmetry is there. Geometrical symmetry means if this I want to analyze this structure, if I can say that that is symmetrical about this plane, dashed plane, which is passing through in between of these two legs, then we can say that there is geometrical symmetry in the system. Okay, and apart from that, the second condition is that there should be loading symmetry and anti-symmetry. So the load which is applied here, okay, that should be there on the both the side means, and the load should also be symmetry about this plane, or the boundary conditions should also be symmetric about this plane. Then instead of modeling the whole system, I can model the half of the system, and on the cut plane, I can mention some special boundary conditions that in case of symmetry problems, symmetry boundary condition, I can mention that this on this plane, the in-plane movement is free and out-of-plane movement is fixed. Okay. Similarly, in case of anti-symmetry boundary conditions, which is nothing but the reverse of the loading, geometrical symmetry that should also be there. And apart from that, anti-symmetry boundary condition. The anti-symmetry boundary condition is that if I the load should be such that if I replace one load with the other one, the negative of that load that should be there. Means if I take the symmetric load of P here, and if I reverse the direction of the load, if that matches with the loading of applied loading, then I can say that the anti-symmetry loading conditions are there. So in that case, what we can do, instead of applying modeling the whole system and applying the all boundary condition, I can model only the half of the system, and on the cut plane, I can say that I will apply in-plane movement equal to fixed one and out-of-plane movement equal to free. So using these two approaches, I can reduce the size of the problem. Okay. So why I want to reduce the size of the problem? Because the simulation cost, that is directly linked with the computational time and the cost of the computational hardware which we are using. So I want to save the computational time as well as I want to use the cheaper computational hardware for solving these problems. Okay, and the simulation cost, that is directly linked with the number of nodes which are there in the system as well as the degree of freedom per nodes. Okay, so if I reduce the number of nodes, then directly I'm saving the cost. So use of symmetry boundary condition, I can for 2D dimensional problem, I can give you this example. Means suppose this is a kind of hook is there, or a connector is there where the force is applied on one side, and on some of the portion of this side, means which will touch with the counterpart or other part, that I am keeping that side is fixed. Then I can say there is a geometrical plane which is where I can say the structure is symmetrical about that one, and as well as there are some the loading is such that the symmetry condition is maintained. Okay, as well as the boundary condition is such that the symmetry condition, we can say, that is there. So instead of modeling this whole domain, what I can do, I can model only the half of the domain, and on the cut plane, this plane which is passing through the center line of this, there I can apply the out of plane constraints equal to 0 and in plane movement equal to free conditions. Okay, so this is how we can reduce the size of the problem. So same thing, if I already mentioned this one, that if the problem is not lying in 1D area or 2D area, then all other problem are the 3D problems. So if the geometry of the system is very complex and the loading is very complex, and sometimes we are interested in localized stresses, then we have to model the full system, or which is all the actual structures are, those are 3D structure. So we have to model that in our FEM systems. Okay, so in this case also we have these kind of elements, means tetrahedral elements and the hexahedral elements. So tetrahedral can be 4-noded one, which is lower order element, and hexahedral can be of 8-noded one, which is also lower order element. And we have also higher order elements in both the categories. When in tetrahedral categories, we have 20-noded elements, and sorry, we have 1, 2, 3. We have 9-noded element and we have 20-noded higher hexahedral elements. Okay. So apart from that, we have to take care of some important important parameters while meshing the system, means because those are directly linked with the accuracy of the system. So how we can improve the accuracy of the system? We have some already. We have few practical considerations. First is the refinement of the mesh. If what we have seen, if I have the system and if I refine the mesh, I will in that way I can reduce the error. Means I already told that the FEM is an approximate technique. We always will have some kind of error in the system. Okay, that will not be the exact system. So how can I minimize that error? Means I can, first approach is I can refine the mesh. Means if I use more number of elements or more number of nodes in the system, then the error that will be reduced. Means you can say this one, this is the exact solution. And if I and this dark black line is the solution which we are getting from FEM approach. If I increase the number of elements, this is approaching towards the actual solutions. Okay, so refinement of mesh, that is leading to the uh, to the um, to the less error, means in the system. But it is up to us, means if we increase the number of nodes or number of element in the system, what is happening? We are ultimately increasing the cost of the simulation. Okay, so there should be a trade-off between these two. So that is up to us, means what we want, how much error we can say that it's acceptable for us. So other one is the mesh quality. So if we have defined some parameters regarding mesh quality, just like aspect ratio, or uh, um, there are many more, means this the largest angle is also, and the warping ratio is also there. Means these are the parameters which are there for defining the quality of the mesh. So we have to limit or we have to maintain some kind of quality of the mesh to get the accurate resolution. If the quality is not lying in that band of the some band of the parameters are already designed. If our mesh parameters are, our mesh matrices are not lying in that band, then we can say the quality of mesh is not maintained and the solution is not accurate. Okay. So these are some examples of poor mesh quality. Means if the aspect ratio is large, if B dimension is very large as compared to H, then we can say the quality of mesh is very poor. If if we have this rhombus shape element, and if one side of that is very small as compared to other one, then we can say the mesh quality is very poor. And if angle is alpha, I already told, means that is very large, near about 180 degree, then we can say mesh quality is very bad. And similarly, this triangular element, means although we are meshing the domain with the quadrilateral element, what few of the elements out of those those are approaching towards the triangular shape, then we can say the quality of the mesh is very poor. So specific to those elements, we will get the error. So this slide shows the list of the FE softwares or FE projects which are there in the market. Means we have few open source FE project. Famous one are Calculus, Deal 2, Free FEM, Get FEM++, and Phoenix, and Elmer, and Z8. Z88. So these are the freely available codes which are there, which you can use for analyzing your problems. Okay. So apart from that, we have a few commercial tools, FE tools, which are being used by the industry people. This is ANSYS, Abacus. These are two of the most famous ones, which are being widely used among the industry people. And apart from that, we have MSc Nastan, COMSOL, LSDN is basically for explicit problems, and we have Arena also. These are the tools which are there uh, in the market, means, or in the on the website also. Okay. So I think here I want to conclude my talk. Means
Okay.
I think I took 5 minutes more than the assigned one.
Sir, thank you, sir. Thanks for your valuable time. And we'll meet at 2 o'clock, sir. Is it okay, sir? Or will
Yeah, for me that is fine. I'll
Right.
in the next section I will demonstrate a problem, means how we can solve the problem using a FEM package.
Yeah, that's great. Yeah, for the
Okay.
participants,
So
we'll
any
meet at,
question?
yeah, any questions? Yeah, I'll just look at this one because we enabled it like this. Yeah, yeah, yeah. Sir, actually, in one of your slide, maybe one there will be the the stiffness matrix for the bar. Yeah, yeah, yes, sir. Yeah,
Yes,
then
yes, yes.
it
That
is
should be
minus
minus.
minus. Yeah, yeah,
Yeah, that is wrong. Yeah.
yeah, yeah. So that's all,
I
sir.
think I
And
missed. Yeah. Thanks.
yeah,
Thanks for
you
correction.
yeah. So that's all, sir. And the participants has no question as of it.
I
Maybe
know
one.
that is too much
Sir,
for
one
one hour.
question. One question is there. How can we select node? One question is there.
How can I select
Yeah,
the
how can we
nodes?
select the nodes? I'm not sure what is this relevant question or not. But they were posted in the chat box.
How can I can say how I can select the element? That should be the question. Means I
Yeah.
because nodes are linked with the elements. Okay.
Yeah.
Okay. So suppose I want to select the type of the element for two-dimensional problems. So we have these two elements, these two kinds of elements. One is the triangular one, and other one is the quadrilateral one. Okay, so the triangular one. So some of the assumption is that this one is constant strain triangle. Okay, the strain is constant in this case, but here we can get the variable strain. Uh, so while selecting the type of the element, we have to think means whether we want uh, the 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 exact value or how much accuracy we want in terms of strains. So if we want a more accurate strain, then we have to go with the quadrilateral one, and if we can compromise with the accuracy in terms of strains, then we can go with the triangular element. But certainly, more the number of nodes, the cost of the simulation will be high. So that we have to think means how much accuracy and how much cost we want to spend. How much accuracy we want and how much cost we want to spend. We want so I think I
Yes. Yes, sir. Answered. Yeah. So if at all any no questions, then we'll wind up this session, and
okay.
we will meet at 2 for the hands-on session. Some practical scope of the modeling and analysis will be discussed in the afternoon session. Would
Okay.
start at 2. Sir, thank you.
Thank you very much for listening to me. Okay. Thank you.
Yeah, thank you. Thank you. So let us meet at 2. The participants, please join at least 5 minutes before so that we'll start by 2. Thank you.